Hello everyone. Let's study Introduction to Spectroscopy. What is spectroscopy? It's a study of interaction between radiation and matter. So another way to define analytical chemistry is to just say that is the application of spectroscopy to chemical analysis. So history of analytical spectroscopy. In 1666, a researcher called Isaac Newton discovered that white light can be dispersed into constituent colors, and he went ahead and produced the first spectroscope based on lenses, a prism, and a screen. In 1800, Herschel and Ritter showed that infrared and ultraviolet light are part of the spectrum. In 1814, Joseph Fraunhofer noticed that the sun spectrum contains a number of dark lines, developed the diffraction grating. We'll see it. In 1859, Kirchhoff obtained spectra of the elements and explains the sun spectrum. 1870, Maxwell formalized and combined the laws of electricity and magnetism. In 1900 to present, you find that more than 25 Nobel Prizes have been awarded to spectroscopists, including the likes of Lorentz and Zeeman, J. Stark, Dirac and Schrödinger, Pauli, Zewal, the visible spectrum of the sun, as you can see it there. You realize the dark lines, the black lines, which was explained that they are the absorption by elements in the cooler outer region of the star. Continuation, you can see the electromagnetic radiation here. This one here, you can be able to see it. Here it is, the laser pointer. I see this one here, and then each color you see is a specific range of frequencies in this spectrum. So you can be able to see from down here we have the radio waves, which has a very longer wavelength, as we move up to gamma rays, which are very short in wavelength. So for example, if we take a wavelength, for example, of ultraviolet radiation, you will see where the yellow color falls about 570 nanometer. The green color falls about 510 nanometer. The blue color falls about 475 nanometer. The red color falls about 650 nanometer. electromagnetic spectrum. So you will see electromagnetic spectrum. Just for a layman, you would think of it like this. So if this is where we were having the gamma rays, and then this other side is where we were having the radio waves. So the radio waves have very long wavelengths. You would think of them as the soccer field, something of that wavelength, something as big in terms of meters. But look at where the X-ray falls, just like a molecule of water, very tiny, small wavelengths. As we continue like that, you can be able to see the variation in size in terms of wavelength, and where they are applied, you will find that for example, the longer radio waves are the ones that help us to listen to our radios. So you can be able to see AM radio, you can be able to see FM radio. Then the microwave, the ones we use even in our ovens. So microwaves also are used. So microwave we use for radar. Then of course we know that infrared is much used by human being, the infrared region. And then we have the visible, where we use light bulbs and many more. So properties of electromagnetic radiation, we know that it is both wave and particle at the same time. And if you remember, there is a relationship between electric field and magnetic field. And as we continue, see that the wave properties, every wave has a frequency and has amplitude and has a phase. So frequency is equivalent to speed of light divided by wavelength. So you can be able to see here, for example, it means that if we have electromagnetic radiation with shorter wavelength, then it means that the velocity will be high. If this wavelength is longer, then it means that the velocity will be low. You can be able to see that electric field is always perpendicular to magnetic field. So that's just an example there of a polarized radiation. And then if we are talking of interference, we can have two types. There is constructive interference, and when we talk of constructive interference, this is where two waves reinforce each other. Remember the properties of a wave: amplitude, frequency, and so on and so forth. So of course, when you are seeing that we have constructive interference, one thing you can see is that the amplitude is actually increasing. Then destructive interference, when the two waves cancel each other. So two waves can actually cancel each other. That is still what we call interference. So the interaction of radiation and matter. So electromagnetic radiation travel fastest in vacuum, where there is no interference. When not traveling in vacuum, radiation and matter can interact in a number of ways. So that one, the first way of interaction is diffraction. Then we have refraction, then we have scattering, then we have polarization, and then lastly we can have absorption. Very important. Those are very important concepts in spectroscopy because they are all used. Then transmission of radiation, the velocity at which radiation travels through a medium is dependent on the medium itself. If you remember very well those interference. So when a radiation travels through a medium and does not undergo a frequency change, it can be undergoing a permanent energy transfer. So however, radiation can still interact with medium. A radiation, an electromagnetic field, polarizes the electron clouds of an atom in the medium. Polarization is a temporary deformation of the electron cloud. So that is one of the interferences we were talking about, or interaction. So you remember one of the ways that radiation can interact was through refraction. So you know that if you have a medium and that medium electromagnetic radiation passes through it, they will interact. So and we can get the refractive index at the frequency I by taking the speed of light over the velocity of radiation in the medium. So so the refractive index measures the degree of interaction between the radiation and the medium. And you know, for most liquids we have a refractive index going from 1.3 to 1.8. Then solids we have 1.3 to 2.5. So refractive index can be used to identify pure liquid substances. Refraction, when a radiation passes through an interface between two media with different refractive indices, it can abruptly change direction. So that's what we call refraction, and that can be well explained by Snell's law. You can be able to see there, can be able to see this angle theta 1, angle theta 2, and then the medium and the medium. So we can get we can actually work out the refractive index, or what we call the velocity of that particular light, by using the formula, Snell's formula. So Snell's law is a consequence of change in velocity in the media. So refraction always occurs at an interface. Its extent depends on the refractive indices of the media. Diffraction, as well explained by Fraunhofer, diffraction is known as far-field diffraction, parallel beam diffraction, and it is very important in optical microscopy. So the other one called so the far field, we are calling it the Fraunhofer diffraction, and when we are concentrating on near field diffraction, we call it the Fresnel. Then diffraction, Bragg diffraction, multiple slit Fraunhofer diffraction, important for instrument design or crystallography. Then diffraction gratings, this is what led us to diffraction gratings, which is widely used in spectroscopic instrument to separate frequencies. It can be made precisely. Then we have what we call scattering. So relay scattering, if you remember, Raman is using a lot this scattering. So scattering of small amounts of radiation by molecules and atoms whose size is near to the wavelength of the radiation. So if they have light and molecules whose size or wavelength are almost close to each other, they can cause what we call scattering. So mere scattering applies to large particles, involves scattering in different directions, practical use in particle size analysis also, like the zeta potentiometer. Then we have coherent radiation. Coherent radiation fulfills two conditions. It has the same frequency or set of frequencies, and it has a well-defined and constant phase relationship. So coherent radiation is cross-correlated in that the properties of one beam can be used to predict those of other beams. So example of coherent radiation is laser and microwave sources. So what we call the coherent radiation, where we have the same frequency, say the opposite will be incoherent, where the frequencies are not the same. So that is what we are talking about. Incoherent radiation produced by random emission, e.g. individual atoms emitting photons. Actually, sometimes it is coherent, but just to a tiny extent. It is also called a continuous radiation. For example, the filament sources, deuterium lamps, and incandescent light bulbs always give us incoherent radiation. More properties of electromagnetic radiation. So we say that it is wave and particle at the same time, and quantum mechanics develop around the concept of the photon, the elementary unit of radiation. So if you think of a photon or an electromagnetic radiation, the smallest unit of electromagnetic radiation, that is where the field quantum mechanics revolves around. And of course, we can be able to calculate the velocity and also calculate energy using Planck's law, where energy is equivalent to Planck's constant. Energy is equivalent to or directly proportional to velocity. So it means that electromagnetic radiation with high velocity have high energy, just like X-ray. And of course the opposite is true. If we have the likes of radio waves, these ones have very low energy. Then we have absorption and emission. Remember, one of the interference was absorption. So of course when an electron, so we say that if involves energy transfer of electromagnetic radiation to a substance, usually at a specific frequency corresponding to a natural atomic or molecular energies. For example, we know very well that for example, an electron can absorb energy of electromagnetic radiation and is excited to higher state, as you can be able to see. So because it is absorbing energy, it is taken to a level that can accommodate that higher energy that is acquired, and then of course it won't be comfortable there, so it has to release that energy. That is what leads to emission. So energy levels, of course, if this one, now we are starting to talk about electron arrangement in an atom. So several types of quantum mechanical energy levels occur in nature. So we call the electronic energy level, a rotational energy level. There is what we call vibrational, and then it's called nuclear spin. So these concepts are very, very important, very, very important. So for example, electronic energy, this is now where we have the likes of techniques like UVVs. Then we have, let's say, nuclear spin, where we have nuclear magnetic radiation, what we call the nuclear magnetic resonance. Then we have vibrational, which also we talk of the IR, vibrational, and much more. So for each of these discrete quantum state and energy driven transitions between these states can be studied, as opposed to continuous range of energies. So that tells us that discrete or discrete quantum states very key to spectroscopy. Derived from transition movement integrals, usually via symmetry arguments that express which energy level transitions are allowed. Some of the energy level transitions are not allowed. So example for rotational energy levels of a rigid linear rotor, such as a diatomic molecule. So a forbidden transition is usually still possible, but often is weak than allowed transition. The uncertainty of measurements, because the lifetime of quantum states can persist for a short period, it can be difficult to measure their energies accurately. This is usually stated in the form of energy time uncertainty. and for that reason so the uncertainty principle, it is not possible to know both the location and the momentum of a particle exactly, a fundamental limit on all measurements. So if you know the location, you cannot also know the moment, because moment is when it is moving and location is when it is standstill. So if you either want to know the location, you forgo moment. Then Heisenberg's terms, the act of measuring a particle's position affects its momentum and vice versa. That is explained by this equation here. In other words, if you know the position of a particle to be within x, then you can specify its momentum along x to apx. And Spectra and Spectrometers. Spectra are usually plotted as frequencies versus amplitude. Instead of frequency, wavelength or energy can also be used. The choice of x and y axis is often dependent on the particular technique. In most techniques, a key parameter is the frequency, stroke energy, wavelength, resolution. So spectrometers these are just instruments that measure the interaction of radiation with matter. So the properties of such interaction can be studied. So spectroscopy in analytical chemistry, widely used approach for characterizing systems ranging from chemical physics to biology, from individual atoms to largest molecules. Some of the most common techniques are the ultraviolet, visible spectroscopy, the fluorescence spectroscopy, infrared spectroscopy, Raman spectroscopy, X-ray spectroscopy, nuclear magnetic resonance spectroscopy. Then we have the EPR spectroscopy. So more of the readings you can do with Atkins and Feldman. The optical property of solids, you can see those ones.